Today's day 6 of Unit 5. So we started today just with the lesson, taking notes. So these first 4 graphs, you want to get those in your notes. So the directions here were to state the number of zeros or roots. So if I look here, that means how many times is this graph crossing the x-axis? So I can see 2 roots, which means, I can see it crossing the x-axis twice, which means there are 2 real roots. On the other hand, number 2, I see crossing 3 times, so 3 real roots. Now, 3 and 4, even though the shape looks the same, we see a parabola and a polynomial, a cubic, they have different numbers of real roots than the original one. So here we had 2 because it was crossing the x-axis twice. Well, on the other hand, this one, even though it has the same shape, if I knew the equation for this parabola and I set it equal to 0 and solved for x, I would get 2 complex numbers. And we know that from the previous unit that would happen. And so because I'm getting 2 complex numbers, we don't see the parabola crossing the x-axis, which means that there are 2 complex roots. And there are 0 real roots. So if I apply that same thinking to this one, this cubic polynomial, I know there's 1 real because I can see right there that it's crossing the x-axis, but there's still 3 total roots. It's just that this U shape that's not touching or crossing the x-axis, that accounts for the 2 complex roots. Okay, so again, if you have a U that's either above or below the x-axis, I could have one down here, that would also be 2 complex. But if you have a U shape that's not touching and or crossing the x-axis, then there are 2 complex roots as part of that U. And in this one again, there's 1 real. So same thing here, we're listing the number of real roots and the number of complex roots. This crosses 3 times, there are 3 real and there are 0 complex. Now A, this is touching here, it's bouncing, and that's through. So there's 2 different spots that it's touching or crossing the x-axis. So that means there's 2 real roots. Now, I don't see any U's that are not touching or crossing the x-axis, so we have 0 complex in this one. Now, you should always be able to check, like if I go back to this one a minute, the degree should match with the number of roots. And so remember to check the minimum degree, I count the directions 1, 2, 3. So it's 3 and there are 3 reals. So the degree matches. Now on the other hand, on this one, when we're checking to see if we found all of the roots, it's again degree 3, but I'm only seeing 2 real roots and 0 complex. The reason for that is because this 1 real root is a double root. Remember, we talked about that earlier in the unit in the lab that we did. We discovered that when the degree is higher than the number of total roots, that's because some of the roots are triple or double roots. So that's why. So when I'm checking to make sure I have all of them, I am going to count the 1 single root right here, but I'm going to count the double root. I'm going to count it as 2 for just a moment for me counting to making sure I have all of them. I count it as 2 plus the 1 single, that means 3, and that helps me know I have all of the roots. But still, when you're listing how many roots there are, we wouldn't say 3, we would say 2 real roots. It's just that one of them is a double, which is accounting for that 3rd root. So 2 real roots, 1 that's a single, 1 that's a double. So the next one, I see crossing the x-axis once, so 1 real. And the second is from this U here that's not touching or crossing the x-axis, so that's 2 complex. Now, this other piece here, don't get confused, that's not a U shape because it's just connecting the single root to the complex root. So it's just connecting that U to the basically a line. It's a line and a U connected. That rounded piece there does not make another U. It's just two complex and one single real root. Next, I just had students figure those out, so take a moment, look at those. Looks like we have 4 real roots and 0 complex. And the last one, 2 real, and from this U right there, 2 complex. And again, there's not 2 U's there. That is just connecting this U, which is crossing the x-axis, to this U, which is not crossing the x-axis. So 2 real and 2 complex. Okay, next I want you to work on page 13, question 1, just A and B. We just did those kind of, I just had students work on those in class. It's basically just drawing a sketch given a specific number of real and complex roots. So I'm not really going to take time to go over that. I didn't really go over that in class. I was just take a minute, work on those. That problem will be on the answer key on Monday. So next, so this, you want to put this in your notes. This is writing the equation of a polynomial. We did something similar to this last class where we had a graph. We looked to see where the graph crossed the x-axis, and then we wrote the factors from there, and then we wrote the equation. And remember, we did that both with a possible equation and an exact equation when we were given another point. In this problem, we're not given another point, we're just given the roots. So it's similar to that, similar to how we started those. The only difference being now we were given an imaginary root as well. So I'm going to start with y equals, so I know that it's crossing at -4, which means we always put x minus in front of that. So the factor is x minus -4, which is just x plus 4. Okay, and then I'm going to do the same thing with 3i, so I put x minus in front of that, and that gives me -3i. Now, one thing I want to point out a minute, and I sort of mentioned this before, but I'm going to go back a slide or two here. Remember that anytime we see that U shape that's not touching or crossing the x-axis, we said there's 2 complex roots, okay? And the reason that that happens is because, this goes back to something we talked about in the previous unit, complex roots always come in pairs. So they come 2 at a time. So you'll never have odd numbers of complex roots. You won't have 1, 3, 5, 7 numbers of complex roots. You only have 2, 4, 6, 8, so forth, numbers of complex roots. And the reason for that is because, and again, we talked about this in the previous unit, because complex numbers have what we call conjugates. So if a plus bi is the root, then its conjugate is a minus bi. So those conjugates will always be there. They'll always exist. They come in pairs. So back to our problem. I gave you in the problem 3i is a root, but you automatically know that that 3i is not the only complex root because they come in pairs. They don't come singly. So even though I wasn't told this, you know that -3i is also a root because -3i is the conjugate of positive 3i. So I need to also include x minus -3i, which is x plus 3i. So now I'm going to multiply. And when I multiply this out, because I have to put it in standard form, I'm going to be smart about it, and I'm going to do the 2 that involve complex numbers first. And hopefully you remember why that is. That's because we have numbers that are going to cancel each other out. The outer 3ix and the inner -3ix are going to cancel out. So when I do first times first, I'm getting x squared. Last times last, I'm getting -9i squared. But of course, I can simplify -9i squared to -9 times -1, which is +9. So I'm going to write plus 9. So then next I'll multiply the binomials, so x squared times x, and when I do that I'm trying to be careful to make sure it goes in standard form, which is highest power first, then decreasing. So x squared times x is x cubed. Then I have with the inners 4 times x squared and 9 times x. Well, I want 4x squared first, so plus 4x squared, and then plus 9x, and then 4 times 9 is 36. So there's my equation in standard form. Now, a couple things you want to think about when you get to what you think is your final answer. Two things. First of all, check the degree. It's cubic, it's degree 3. I should have started with 3 roots. So if I had 4 roots and I'm ending up with something that's cubic, I know I did something wrong. I should have the same number of roots as degree and vice versa. The second thing you're going to check is that the coefficients should be real numbers only. You should not have things like 2i(x cubed). If you have imaginary numbers for coefficients, then you know that you did something wrong. And the reason that you know you did something wrong is because, remember, when we're multiplying the complex conjugates together, that canceling out is always going to happen. So the imaginary part goes away, and then you're just left with real numbers. So if you have any coefficients that are imaginary or complex, then you did something wrong, and go back and find your mistake. Probably, if you do get that, it's probably that you forgot about the conjugate, including that as a root, or possibly you multiplied them incorrectly. So that's our final answer. So let's try a few more. So I'm going to start with looking at the root. I'm going to write y equals, if 2 is the root, then x minus 2 is the factor. So I have negative 2 minus 2i. So again, I'm putting x minus in front of that. Now I'm not trying to do too much in my head all at once. I'm just putting x minus in front, and then I'm copying that, negative 2 minus 2i. And then lastly, I need to figure out what the conjugate is. Well, the conjugate of negative 2 minus 2i is negative 2 plus 2i. Remember, the conjugate, the a stays the same, so negative 2 stays, but the sign in between the a and the b changes. So if it was minus, it becomes plus. So anyway, back to our problem. We're going to put x minus in front of that root, negative 2 plus 2i. And of course, I'm going to simplify that, clean it up a little bit before I multiply. So I have y equals, I'm keeping the x minus 2 there. I'm going to distribute those negatives. And I'm getting x plus 2 plus 2i. And I'm getting x plus 2 minus 2i. So once again, I have 3 different terms and I'm multiplying. I can multiply in any order I want, but probably the best order would be these 2 first. So I have a trinomial and a trinomial, either distributive property, or if you want to use a generic rectangle to help you with that distributive property, you can. So I have x plus 2 plus 2i and x plus 2 minus 2i. So we have x times x, which is x squared. We have x times 2, which is 2x. We have 2i times x, which is 2ix. We have 2 times x, which is 2x. We have 2 times 2, which is 4. We have 2 times 2i, which is 4i. Negative 2i times x is negative 2ix. Negative 2i times 2 is negative 4i. And last, negative 2i times positive 2i is negative 4i squared. So I'm going to combine like terms, but I'm going to clean this up. Negative 4i squared we know means negative 4 times negative 1, which is positive 4. So I'm going to leave my y equals. I'm going to leave my x minus 2. I get x squared. The 2x's combined to give me 4x. The 2ix and the negative 2ix cancel out. The negative 4i and the 4i cancel out. And then I have the 4 from the negative 4i squared, and I have the 4. So I'm going to combine the 4 and the 4, and that's going to give me 8. So that's what I have from multiplying x plus 2 plus 2i times x plus 2 minus 2i. I get x squared plus 4x plus 8. So now I have a trinomial times a binomial. Again, either distributive property, or you can use a generic rectangle to help you with the distributive property. So we have x squared plus 4x plus 8, and we have x minus 2. So x times x squared is x cubed. 4x times x is 4x squared. 8 times x is 8x. Negative 2 times x squared is negative 2x squared. Negative 2 times 4x is negative 8x. And negative 2 times positive 8 is negative 16. So we have y equals in the front. I have x cubed. I'm going to be careful to put these in decreasing order. So 4x squared plus negative 2x squared gives me a positive 2x squared. I have an 8x minus 8x. They cancel out. And I have minus 16 on the end. That is my equation in standard form. 3 roots, I have degree 3, and I don't have any complex or imaginary coefficients, so I know that it's correct. Next, so same idea, we'll start with y equals. Negative 1 is the root, that means x plus 1 is the factor. 1 minus 2i means I'm putting x minus in front of that. The conjugate of 1 minus 2i is 1 plus 2i. So I'll put the x minus in front of that. I'll go ahead and distribute the minus signs. So x minus 1 plus 2i and x minus 1 minus 2i. So I'm going to go ahead and multiply x minus 1 plus 2i times x minus 1 minus 2i. So x times x is x squared. X times negative 1 is negative 1x. X times 2i is 2ix. Negative 1 times x is negative x. Negative 1 times negative 1 is positive 1. Negative 1 times 2i is negative 2i. Negative 2i times x is negative 2ix. Negative 2i times negative 1 is positive 2i. And negative 2i times positive 2i is negative 4i squared. So negative 4i squared means negative 4 times negative 1, which is 4. X squared is in the front. Negative x plus negative x is negative 2x. 2ix and negative 2ix cancel out. 2i and negative 2i cancel out. And we have a 4 and a 1, which combine to give us 5. And now I just have to do x plus 1 times x squared minus 2x plus 5. So we have x squared minus 2x plus 5 times x plus 1. X times x is x squared. Or I'm sorry, it's x times x squared is x cubed. X times negative 2x is negative 2x squared. X times 5 is 5x. 1 times x squared is x squared. 1 times negative 2x is negative 2x. And 1 times 5 is 5. So we have y equals, we have an x cubed in the front. We have a negative 2x squared and a positive 1x squared, which is negative 1x squared. We have negative 2x and positive 5x, which is positive 3x. And we have a positive 5 on the end. And that is our equation in standard form. 3 roots, degree 3, no complex or imaginary coefficients. It's looking good. Your homework for Monday is to finish up page 13. We did those graphs earlier when we went through the lesson. So finish up page 13, do page 22, and on worksheet number 3, remember we're in Unit 5, problems 15 through 18. Do those for the next class.